Today we're going to talk about chemistry and measurement, more specifically, units, error, accuracy, and precision. So let's take a look at values and scientific measurement. Values from measurements. A value is a quantitative description that includes both a unit and a number. For 100 meters, for example, the meter is a unit by which distance is measured, and the 100 is the number of units contained in that measured distance. So units are quantities defined by standards that people agree to use to compare one event or object to another. The International System of Units, or SI, is very widely adopted across the world. The only countries that haven't officially adopted SI are Liberia in Western Africa and Myanmar, also known as Burma, which is in Southeast Asia. But now they are reportedly using the metric system quite frequently. The United States is really the only significant holdout. We don't use the metric system in our daily lives. We use, instead of kilometers and meters, we use miles, we use inches instead of centimeters, for example. But we did officially adopt the SI unit in 1866. It's just not really incorporated into our daily life. But in science, it is definitely the unit that we use in the United States and throughout the world. The base units for the International System of Measurement are length in meters, mass in grams, time in seconds, and temperature either in degrees Celsius or degrees Kelvin. There's another type of unit that we use frequently in chemistry, and this is called derived units. So these are units of measurement formed by products of the powers of base units. So an example of a derived unit would be area. So when you're calculating area, you multiply the length times the width, and that gives you the value, the derived unit of meters squared. Another would be volume, and that is actually calculated by multiplying length by width by height. So meters times meters times meters, giving you the derived unit of meters cubed. One thing to note as well is that 1 cubic meter is equal to 1,000 liters. So there you go, 1 cubic meter equals 1,000 liters. So one portion of that equals 1 liter. Another thing that we get into when we're looking and talking about SI units are metric prefixes. And so this gives us a little bit more flexibility. So here, for example, you see the kilogram, which is 10 to the third, or 1,000 times a base unit. So you may see this pretty frequently when you hear the word kilogram, right? So the base unit is grams. Gram is a very small unit. So when we're talking about a person's mass, for example, or larger mass, we think of kilograms, right? 1,000 grams. You're going to frequently come across the prefix of centi and milli, so as in centimeter, or millimeter. Also, milliliter is a very frequently used unit of measure. In this course, I want you to be familiar with these prefixes, and you are responsible for knowing the units from kilo to atto. One way, a little mnemonic that can help you to remember these is King Henry died drinking chocolate milk Monday night playing Final Assault, which for those of you that are maybe less into video games is a video game. You may not know that, but it's a little acronym to help you kind of remember those prefixes. So looking at metric units, one of the best or most useful things about metric units is that everything is in powers of 10. So for example, you can see that as we're measuring the height of a skyscraper, we have in kilometers, this skyscraper is 0.35 kilometers. but it's 350,000 millimeters. And then we can compare that to film. So 35 millimeter film, if we adjust that to kilometers, becomes a very, very small number in kilometers. Also looking at this, bottle, this 2-liter bottle of soda, which is measuring volume. Liter is a measure of volume. You can see that you want to select the metric prefix that is most appropriate to the size of that object. Same goes for the weight of this cat, right? Probably kilograms would be the best way to measure this cat. It's a 5-kilogram cat. Perhaps hectograms, right? If you wanted a more accurate measurement, more precise. And then with cherries, however, cherries you might want to measure in grams because this is only 5-gram quantity of cherries. So now let's talk about the various temperature scales that there are. So you are familiar, I'm sure, with Fahrenheit, which is all the way on the right. That is what we use in the United States. But if you are living elsewhere, you are probably frequently see degrees Celsius. And if you have taken a chemistry class before, which I hope that you have as you're taking this course designed as a review, you're familiar with the concept of degrees Kelvin. So Celsius is based on their 0 is the point at which water freezes, right? So 0 degrees Celsius is the point that water freezes. Freezing water is in Kelvin. Water freezes at 273.15 degrees Kelvin, and it freezes at positive 32 degrees Fahrenheit. So you can see that these are just kind of different ways of talking about the same thing. We're still just identifying temperature, and these are just various units for that. Another unit that you may or may not be familiar with is the unit of density. So density is an intensive property, right? So it really depends upon the composition of the substance, right? And so they don't necessarily have to be the same size. So density is a ratio of the mass of an object and its volume, right? So for example, the liquids in this cylinder, and this is a very common density demonstration that is done, the most dense liquids are going to sink to the bottom of this cylinder, while the least dense liquids are going to kind of float to the top, to the surface. So you can see that below, this shows the relative size of approximately 10 grams of each substance that is present here. So we have lithium, aluminum, and lead. And so from that, we can actually calculate their density. So lithium, so we have 10 grams of lithium, and the volume of that cube, so as we said, length times width times height is 19 cubic centimeters cubed. Okay, so the density of that cube of lithium, my apologies, is 0.53 grams per cubic centimeter. For lithium, it's still 10 grams of the same substance, or of a substance, but it's only 3.7 cubic centimeters. And so that is a density of 2.7 grams per cubic centimeter. And the final, which is lead, and you may have heard that lead is very, very heavy. You may hear lead boots make you sink in a river, that sort of thing. And 10 grams of lead takes up very, very little space. It's only going to be 0.88 cubic centimeters. And that has a density of 11 grams per cubic centimeter. Another thing that we want to look at when we're talking about measurement is the idea of accuracy and precision and error. So below me, I have 3 targets, right? And we're attempting to hit the bullseye. So we have 3 arrows in each to shoot, and we're going to analyze each of these different results. So we'll see if after this we can kind of ID what accuracy and precision really means. In this case, the the arrows hit the bullseye all three times, right? And not only do they hit the bullseye, but it's repeatable. So all three arrows hit the bullseye, okay? And so in this case, we would call this both accurate and precise, okay? So accurate because they hit the bullseye, precise because they all hit the bullseye, so it was repeatable. In this next scenario, you can see we don't hit the bullseye, but our arrows all land in the same relative spot. Okay, so this one we would say it's precise because it's repetitive. They're getting the same result each time, but they're not accurate. Okay, they are not hitting the bullseye. In this last scenario, we would say that this is neither accurate nor precise, okay? And so in this case, you see, for one, none of the arrows are close to the bullseye. And second, none of the arrows are really close to each other. There's no repeatability in these results. So it's neither accurate nor precise. So to give you a working definition, precision describes how closely a series of measurements of the same object resemble each other. So in science, we do a lot of trials, right? And so we want those trials to be relatively close together. And so if you, for example, you measure something and it's 1.1 grams, 1.1 grams, 1.1 grams, that's very precise measurement. Doesn't necessarily mean that it is correct. So the closer the measurements are to each other, the more precise those measurements are. The precision of a measurement is not necessarily equal to its accuracy. Okay, so that's what I was saying when it does not necessarily mean that it is correct. What accuracy outlines or details, however, is a measurement's relationship to the property's true value. So, for example, when we were measuring the density of lead, if we were to weigh and measure that sample repeatedly and we got the same density over and over again, and say we got a density of 15 grams per cubic centimeter, and we got it three times in a row, we'd say, well, that was pretty precise. Our measurements were pretty precise. But when we compare that to the known value of 11 grams per cubic centimeter of lead that is out there, we know that it really wasn't that accurate. Actually, it was quite off. But that is the definition of accuracy and precision.